Hey folks, Chapter 8, Section 1, 8.1. New stuff, lecture, online, okay. I think you're going to find 8.1 is pretty manageable. So let's use our familiar example of salmon. Let's pretend we magically know that the average length of a salmon is 20 inches and a standard deviation of 4 inches. So we just magically know this for some reason. And if I were to draw a picture of it, it would look something like this. Go back 16. So the standard deviation is technically 4 inches. So most of the salmon are between 16 and 24 inches, about 68% of them, but we'll say a majority of the salmon are between 16 and 24. So notice whenever we're thinking about this, we're looking at one salmon at a time. So 8.1 is all about the idea of what if you look at more than one at a time? What if your sample size is greater than one? So let's say we were to sample something like 16 salmon. So imagine if I were to look at 16 salmon, that's a lot of them. And so maybe you get a randomly really big salmon, you'd probably get a randomly really small salmon. So the X bar, the average of 16 salmon, should be really, really close to 20. So if we were to draw that, so imagine if I were to draw a similar picture. If I were to look at 16 salmon, a group of 16 salmon, and look at their X bar, the mean X bar should be really, really close to 20. So much so that these numbers are technically correct, but just go along with it for now, that most of the X bars, if we were to look at a sample of 16 salmon, they would be really, really close to 20, probably most of the time between 19 and 21. That's when I'm looking at 16 salmon at a time. Okay, so that's the main idea. What if I was able to look at every single salmon? So if I was able to look at every single salmon on the planet, magically, and the average, the X bar, by definition, would be 20. So all the average, if I talk to every single salmon, by definition, would have to be 20. So if I were to draw a picture, it wouldn't be very good, but imagine a bell curve looks something like that. It wouldn't even be a bell curve. It would just be a straight line up and down because the X bar is 20. Okay, so that's the first idea. The main idea is the more and more salmon I talk to, the bigger and bigger my sample size is, it should get closer and closer to that mean of 20. Okay. So, let's see. So mathematically, here's the idea. We learned a formula before the test, z equals x minus mu over sigma. So this happens to be the formula if we're only talking to one salmon, a simple random sample of size 1. So if n is more than 1, then the formula is x bar minus mu sub x bar all over sigma sub x bar, which, just go with this for a few, is just x bar minus mu over sigma over root n. So let's say you're good at patterns. Chapter 8, Section 1 is just this formula. So on the last test, you just use this formula. All we need to do is now incorporate sample size into all of our equations. That's it. So if you're good at patterns, I could just say, hey, here's the new formula. Go ahead and just figure everything out, and you should be able to. But let's do some problems. There's a little worksheet. Make sure you have that worksheet. So I just want to point something out really quickly while I have this. The mean of the X bars is just mu, and then the sigma sub x bar is just sigma over root n. And this guy we call the standard error of the mean. They like to give everything a complicated name. Standard error. I hate that they use the word error because it sounds like a mistake. I'd say they should have come up with a better name, but they didn't. Standard error of the mean. I like to just call it, what's our new standard deviation? Oh, it's sigma over root n. Oh, okay. You mean because I need to account for sample size? Yes. So maybe just right here, I'll write down that the mean of the x bars is just equal to mu, and then the standard deviation of the x bars is just the standard deviation over the square root of n. Okay. I'm going to pause right there, and then I'll do another little video, and then we'll get into the worksheet. I hope it's going so far so good.